In this exercise, we're going to consider both convection and conduction in terms of heat transfer. So the problem is that the window of a car, which is 4 millimeters thick, is defogged by passing warm air at 40 degrees C over the inner surface, and you're told that the convection coefficient is 30 watts per meter squared Kelvin. And the for conditions when the outside ambient air temperature is minus 10 degrees C, and the associated convection coefficient is 65 watts per meter squared Kelvin. What are the inner and outer surface temperatures of the window? And you're told the thermal conductivity of the glass is 1.4 watts per meter per Kelvin. So again, the way you start this is draw a sketch. So this is the inside of the window, so you're passing warm air over at 40 degrees C, and you've got the convective heat transfer coefficient, thickness of the glass, the inside temperature, surface temperature, and the temperature on the surface on the outside, and that's air is passing over at minus 10, and here heat transfers from left to right. And again, drawn as an analogous to an electrical circuit, you're going from the bulk fluid temperature on the inside with this thermal resistance to the surface temperature on the inside, then through the window with this thermal resistance to the outside, and then back to the bulk fluid temperature on the outside. So how do we solve this? Well, first of all, we don't know anything about the surface temperatures on the inside or the outside, but we do know the bulk fluid temperature, so we have to use this thermal transmittance value, this U value. And we're not told the area, but it doesn't matter because we can work entirely in terms of heat flux rather than total heat transfer. So first of all, we need to find out the U value. So remembering that 1 over the U value is the sum of 1 over the convective heat transfers and the radiative heat transfers, plus the sum of the distance over the thermal conductivity. And here there's no radiation, so those terms disappear, so this is what that term's equal to. And if we plug in the numbers, do the sums, we come up with this value, but that's not what we want. We take the inverse of that, so the U value is 19.4 watts per meter squared Kelvin, for the whole system, if you want to think about it like that. So therefore, if we now substitute the inside temperature and the outside temperatures, remembering to put the minus sign in there, then we end up with a total heat flux of around 970 watts per meter squared. So now we know this, and we know that that's the heat flux going through the window in its steady state, so we know that's the heat flux at any point through the system. We can now use that to work out the inside and the outside temperature. So the heat flux must be constant, so we can use this formula now that the heat flux is equal to the convective coefficient times the change in temperature. So for the inside window, it's 40 minus the heat transfer, the heat flux divided by the heat transfer coefficient. And if you work that out, it comes out at 7.6 degrees C. And similarly for the outside of the window, you can use the same equation and rearrange and plug in the values, and you should get a value of just around 5 degrees C for the outside temperature of the window.